Hi, I'm Andy Welton, and I'll be guiding you through a case study we conducted at Purdue University for a single-family home that is the most monitored home in America. There are 3 different peer-reviewed journal articles that you can access for some of the details about this study. As I mentioned, this home we refer to as the most monitored home in America. This is a 3-bedroom, 1.5 bath home in Indiana with water-saving fixtures that was renovated in 2014. It has a trunk and branch plumbing design, and I'll explain what that is in a second. It also has PEX piping. There are thermocouples throughout the entire plumbing system. What that means is that we can tell the water temperature throughout the entire plumbing system at the fixtures as well as through the piping system, the hot and cold water systems. We also know the indoor air temperature every second of every day, flow rates at every fixture every second of every day, energy used per device, and during our study, which was 1 year in duration, we went into the building at least 58 times and collected water samples like you normally would take a water sample. But because of our online monitoring capability, we're able to accumulate over 600 million online water quality and temperature plumbing measurements. Now, this home receives water from a typical public water supplier that is regulated by the state. They use a groundwater source, which has high in calcium magnesium hardness, and chlorine is their disinfectant residual. So this is free chlorine. They serve about 31,000 people. In the distribution system, this building is located miles from their water treatment plant. So where they treat the water and they put it into the distribution system to send it out to their customers, the water has to travel miles before it gets to this study home. They have a consumer comps report that describes the utility's water quality test that the utility does on the source water and the water that they're putting into the distribution system, as well as some select locations throughout their system. In Indiana, 0.2 milligram per liter of chlorine is the legally detectable disinfectant level, which means that the public water system must have 0.2 milligram per liter of chlorine in their distribution system before it is delivered to the customer. Testing is conducted by the public water system, as I mentioned, at the point of entry to the distribution system and at several locations around the system, but no public water system really tests at the service lines. First of all, it's not legally required. And second of all, to my knowledge, nobody ever does that because you would have to test right at a water meter connection. So as I mentioned, the plumbing had a trunk and branch design, and the study was conducted several years after the building was built. What we have on the right-hand side is just a depiction of the roadway, and underneath the roadway was a buried water main. So this was a PVC water main, and the water flowed onto the private property, but it went through a utility service line, so a pipe that connects the PVC water main to the water meter, then the water meter, and then after the water passes the water meter, it goes to a pipe that connects the water meter to the building itself. So that's called the property service line. So the home had 3 floors. It had a basement, a first floor, and a second floor. And if you were to just walk into the home, what you would see is a number of things that you would normally recognize. You would see washing machine, you would see a dishwasher, bathroom sink, bar sink, kitchen sink, water heater, and a number of other types of appliances and devices. So the water comes in at the basement and it goes to a water softener. So all the water in the building gets treated by this water softener. And then from there, the water then goes to the cold water plumbing system. So here it goes through a series of pipes that take it to different fixtures, and it takes it also to the water heater. So cold water is delivered to the water heater. What's important to point out is this is called a trunk and branch design. This is where you have a main trunk line. So the water goes, say, from the water softener to the bathroom shower. And you can see that single line going up. That would be the trunk of the system. And the branches are the smaller segments that branch off that trunk to the fixtures. Now, there's also hot water in the system, and hot water is generated in the water heaters. And so what we have here is a water heating system. And so the red pipes depicted here convey water to different devices, and this conveys hot water. There's an interesting approach in the bathroom on the first floor and the bathroom on the second floor. As you can see, there's purple colored symbols, and that indicates a mixing valve here. And so what happens is cold and hot water come in to these devices, and then there's a single valve that you turn. There's not two different handles, there's one valve. And that means that the water is mixed, cold and hot water is mixed behind the wall where you can't see it. And then that water is dispensed. So this is the building plumbing system that we studied. Now, all the water that enters the home went through a service line. And on the left here, you can see kind of a picture of a pipe coming through the wall and then going upwards. And then there's a kind of cable that comes off it. That cable is measuring the pressure differential that's happening at the service line. But we also take some of that water and we send it through this online monitoring device. And so we can measure pH, turbidity, water temperature, as well as disinfectant level concentration every minute of every day if we'd like to. And we did to some degree. Also, behind the walls on the right-hand side, you can see flow meters. And these flow meters are connected to a data acquisition system. And we could, again, as I mentioned, measure the flow rate at every point in this plumbing system at any time during the study period. So to understand water safety at a building faucet, we need to be able to answer several questions. And first, how variable is the product being delivered to the building by the public water system? And so sometimes people assume that the water being delivered by the public water utility is always the same quality. And if it is, well, then the water quality that we find at the faucet, if that's different, then clearly that difference can be attributed to the plumbing system only. Another question we need to ask is, how does fixture use relate to chemical and microbiological characteristics of the water? And does it matter how frequently we use a fixture? What if we left that fixture sit for 6 days? Would we have the same chemical characteristics of the water? Would we have different ones? You know, what role does fixture use play? And then the third question we have is, are there certain seasons or times of day or days of week that you are more likely to find contaminants of concern at your water fixtures, whether they be your drinking water fixtures, your kitchen sink, or your shower head? And so some of the parameters that we looked at were water pH, disinfectant concentration, organic carbon. And organic carbon is just a summation of all the organic material in the water, heavy metals like lead and copper and zinc and some others, as well as disinfectant byproducts. And disinfectant byproducts are chemicals that are accidentally produced when you have chlorine in the water. So these are not produced on purpose, but as chlorine is in drinking water, it reacts with organic material in the water and produces these things that are byproducts and not intended to be there. But they are regulated, so we're concerned about whether or not they're produced more so in a building or not. Some other parameters that we were interested in about, heterotrophic plate count. This is basically just a surrogate bacteria indicator. Total cell count, another way to indirectly measure bacterial levels in water. Legionella species and Mycobacterium species as well. And so there's a number of other water quality tests that we conducted, and you can read more about those in the papers. So our results. What we found was that building seasonal total water use was pretty much consistent. And so if you look on the left-hand column, we see season and water use characteristics. And so on the far left, we see the seasons, fall, winter, spring, and summer. These, in the number in there, right after the season, indicates on average how many people were inside the home per day. And so you'll see like 2.2 persons or 2.8 persons. And this is just averaged out over the entire season. Then you see the total volume line, and what we see for the service line, so the water entering the building, how much water passed through that service line enter the building, it's pretty much consistent per season. But what we do next, though, is we'll look at the fixtures. In the fixtures, however, if we look at the second floor shower, for example, the total volume in fall that was used was about 8.1 cubic meters. In winter, it was 7.3. But then you see drastic changes in spring and summer. And so we do have different water usage at the same fixture. And the question is, does that precipitate changes in water quality at that fixture? How do we use our plumbing? Does it impact that? So we did find high seasonal variability for specific fixtures. And then if you want to take a look, sometimes these fixtures sat for 100 plus hours, sometimes even 6 days before they were used. And that's because people sometimes travel away from their homes. So it's really interesting to see that this is real data that's generated just in a single family home, and there's different use frequencies, or water is sitting behind the walls in pipes for different amounts of time. The question is, does that impact water quality? So before we get too deep into the house, I do want to bring your attention to this discovery. In this discovery, by testing the service line every minute of the day for 1 week, we found the same quality of drinking water was not delivered to the building all the time. So let me show you here. If you look on the right in this figure, at the very bottom, there's the date on the x-axis, and then on the y-axis, there's different water quality characteristics. Chlorine is the disinfectant. And so what we see looking from left to right is it kind of looks like a mountain range. And what that is the running average of the chlorine concentration. So sometimes there was 1.8, 1.9 milligram per liter of chlorine detected at the service line, and other times it went to 0. It was not detected. What we'll bring your attention to also for the turb graph, or the turbidity, which is just a measure of particles in the water. Sometimes there's spikes, right? And so sometimes it's 0, but then it jumps up to 2.5 or 2.7 NTU. And so this indicates that there might have been particles in the water that were being detected, but often there really wasn't detectable levels. And then if you look at the very top graph, you see flow rate. And what we see is that flow rate for the building water system changed over time, and this is expected because water is not constantly flowing through the building. Sometimes it's flowing at higher flow rates than others. So what we did, though, is we looked at these turbidity peaks, these particle peaks, and what we found out was that flow rate, the times when there was high flow sometimes corresponded to when there was higher amounts of particles in the water. And so what that might mean is that when you have a lot of water flowing through your pipes, you may be scouring scale, this material or sediment that's kind of built up on the inside of the pipes and becomes dislodged and then moves through the plumbing. Another interesting concept here is that when we did sampling, we found that in summer, about 25% of the time, the building was not receiving chlorinated water. They're receiving water from the water distribution system, from the public water supply, but it didn't have any chlorine in it. And in winter, about 6% of the time, the water didn't have any chlorine in it. And the reason why this might be is because chlorine degrades faster at warmer temperatures. And the water inside the buried water distribution system warms up in the summer compared to the winter. So this is really interesting because it implies that we can't necessarily assume that the water is always going to be the same delivered to a customer from a public water utility. And then looking more closely at some of the other data that we published, water quality at the service line varied by season, time of day, and day of week. So moving on to organic carbon, what we found is that organic carbon levels were often greatest in the cold water plumbing. And so one of the typical theories is that we have a hot water heating system, and when we send that hot water out into the plumbing, it will cool behind the walls, right, inside those pipes. And hot water heating systems generally don't have much chlorine in them because the hot water increases the decay rate of chlorine. And so our theory, or our assumption, was that we're going to see more organic carbon or material in hot water instead of cold water. And that's actually the reverse of what we found. So the hot water concentrations coming in to the building, or excuse me, the hot water concentrations of total organic carbon maxed out at about 5 milligram per liter. So generally about 0.5 to 2 is average, and from what we've seen in other buildings and other communities across the country. But what we see here is the cold water system jumped up to about 60 milligram per liter during the summer in springtime. So there was something definitely going on with carbon in the system here. One of the reasons why we're concerned about carbon typically is because sometimes carbon is dissolved and it can be used by bacteria to grow. And we generally don't want that to happen because we don't want to feed the organisms in the plumbing where they may proliferate and pose water quality aesthetic problems or actually human health problems. Some other conclusions that we have, if you looked at chemical and microbial levels in the building and you go to fixtures in different rooms, whether you're in the bathroom or the kitchen or downstairs in the laundry room or upstairs in the shower, water quality differed by room to room, time of day, day of week, and by season. So this is, not necessarily unexpected, but the extent of differences that we found were significant. And what I mean by that is, water entering the building at a pH of about 7.2, and utilities that provide water to residential customers typically have a stable pH. But once that water entered the building, it consistently increased in pH to 9.4. And why is that important? Well, as you increase the pH, you can cause heavy metals to basically precipitate out of solution and start coating the inside of your plumbing system. So these changes that happen inside building plumbing due to pH or some of the other basic characteristics can potentially have a profound impact on the quality of water and, say, the heavy metal content of that water that reaches the faucet. For more than 85% of the testing that we conducted, no disinfectant residual was found exiting the second floor bathroom sink cold fixture. That's important because cold fixtures are generally used for drinking water. We also found that chlorine was generally not found in the water heater, and it wasn't found in other hot water fixtures. And that's not surprising in that hot water heaters generally facilitate chlorine decay. Now, disinfectant byproduct levels, as I mentioned, these chemicals that react with chlorine in the water just naturally, they were entering the building at a pretty low concentration, but sometimes they increased by about 89% in the building. And this is due to the warmer temperatures in the building. So when the water comes into the building, it generally warms up to room temperature, like the temperature of the building. And there's chlorine in contact with it, and there's time, right? The water is sitting behind the walls, under your feet, in these pipes. We did see spring and summer nitrification inside the hot water plumbing. And nitrification is a process where you have ammonia that's converted to nitrate by bacteria. And what we did was we did testing for ammonia in the service line water, and sometimes the utility has low levels of ammonia present. And then when that water came into the building, it was transformed into nitrate and low levels of nitrate, but it was happening. And so we can have bacteria in the building that take the water that's delivered to the building and then transform it into something else, or create contaminants that were not necessarily present before. So this was a discovery that was important. And then there's several other organisms that we detected. Mycobacterium species and Legionella species levels were lowest at the service line. So these organisms were present in the water being delivered, but inside the building, they were amplified. So there was much more concentration of these organisms. We did see, though, that there was seasonal variability to the magnitude of, say, Legionella species at the service line. So during the summer, they were in greatest abundance compared to the winter when that was the least abundant season for these organisms. Mycobacterium avium, we saw them at greatest abundance in the summer, whereas in the fall, they were not as great in magnitude. And why that matters for sampling is if you're going to try to find these pathogenic-like organisms or classes of organisms in the water, you need to have some idea about, when's the best chance to find them. So if we conducted the study, say, in the winter and didn't find Legionella species at significant levels, for example, does that mean that the summer months would have the same response? And the evidence here shows no. So you'd actually want to conduct your study during the summer so that you could increase the chances of finding that potential class of organisms. And then finally, inside the building, all fixtures had bacteria, but hot water fixtures generally had higher bacteria. So in terms of lessons learned from this study, water delivered by the public water supplier varied in quality. And so the same water of the same composition, chemical composition and microbial composition wasn't consistently delivered. And that's important because if the water that's entering the building is not of a consistent product quality, then you can't expect that even if that water was to be, say, delivered straight through the plumbing to all the fixtures at once with no changes, that the water would be the same at those fixtures, right? Water pH was consistent, being delivered to the property, but disinfectant was sometimes not present up to 25% of the time. And then Legionella species and Mycobacterium species were both present in water being delivered to the property, and their magnitudes varied by season. Now, inside the building, chemical and microbial levels differed room to room. Water quality varied by season, across fixtures, time of day, and day of week. And so this really raises questions about how do you sample a building to find possible contaminants of concern if you don't know how variable water quality is at these locations. And so there's some probably frequency of testing that you're going to have to do to better understand how water quality changes in these buildings. Drastic pH increases occurred, disinfectant byproduct increases were found, and these were somewhat surprising. Cold water contained more organic material than hot water. We did find bacteria classes that were present, but they varied by season and hot versus cold water fixtures. We did find that stagnation time influenced some of the differences, and different fixture use patterns influence the results. So really, when it comes down to it, when investigating the safety of water in a building plumbing system, one must consider that the water being delivered to that building is not of consistent quality sometimes. The plumbing system, how it's designed, may impact the results. How the system is operated may impact the results. And fixture use must be considered. So all these considerations must be factored in for determining water safety in a single family home. You can extend these type of learnings to commercial buildings. Think about larger buildings where you have a 50-story high-rise or a 4-story hospital. All these factors likely become more complex in these larger buildings. And that is why we need to understand building plumbing systems and relate plumbing design, operation, fixture use, and water quality to protection of public health in these buildings. Thank you very much. If you have any questions, please don't hesitate to contact me, and have a great day.